Observing how stars and galaxies change brightness over time is very important in astronomy. For some astronomical objects, changing brightness can be graphed as a periodic function, or a wave. A periodic function is one that repeats itself. We're going to play a sonified version of a periodic function. The higher in pitch the note is, the higher up on the y-axis the point is. Listen. Scientists obtain information about periodic functions by measuring different characteristics of the wave. The first one is period. That is how long it takes to get from one peak of the graph to the next. Listen to how the sound of this graph starts high, goes low, and then goes high again. The time between the two high points is the period. Another measurement is called amplitude. Amplitude is the difference between the highest or lowest point of the wave to its midpoint. To hear this, we first mark the midpoint between the two extremes with a tone. Listen for that now. If we place a marker at the highest point and one at the midpoint, we should be able to hear the difference. The amplitude is the difference or distance between the two tones. In an ideal world, we would be able to make measurements of variable objects day and night, and all the light measurements, or photometry, would be accurate. The resulting light curves would be perfect sine waves, sounding much like the curve we've been listening to. Hear it one more time. In reality, however, astronomers run into many issues when observing variable objects. The data might be altered by noise, a kind of error coming from changes in the atmosphere, or from the instruments themselves. Listen to how noise alters the data. Additionally, there are gaps in the data because we can only take measurements at night. And on top of that, we can't observe all the time. Other people need to use the telescopes too. This inconsistency makes our data even more patchy. With all of these complications, we've gone from this data to this. So far, we've been listening to about 2 days worth of data. Let's add a few more days so we have more information to work with. This spotty sample makes it difficult to identify the period of the curve. However, if we know that the data should be periodic, we can figure it out using a technique called period folding. Period folding works by breaking up the x-axis into equal sections. The size of these sections is our best estimate as to what the period might be. The sections are then stacked, or folded, on top of each other. When the period we choose is correct, the data line up to create one continuous curve. Imagine we pick a period of 1 day. Every time 24 hours passes along the x-axis, we mark it off. Listen to our spotty data again. This time, we will play a sound at each 24-hour mark. To fold the data, we keep the first section of 24 hours right where it is, but the 24 to 48-hour rectangle is going to be picked up and moved on top of the 24-hour rectangle, and the 48 to 72-hour rectangle is going to be put on top of that. We keep doing this until all the data points are plotted one on top of another. We're going to slow down the stacked data a bit so you can hear the individual points. Listen to what the data sound like now. Hear how they're all jumbled up? This tells us that the period is definitely not one day. Let's unfold the data and start again. Let's try a period of 0.51 days. Listen. This one sounds just a little different. The data still sounds jumbled together, but if you listen very closely, you can hear a patch in the latter half of the audio where there are fewer low pitches. This isn't quite the correct period, but we're on the right track. Here is what a period of 0.52 days sounds like. The increase and decrease is even more clear with this one. It's getting better. Let's make a few more guesses. Here is what a period of 0.53 days sounds like. Different, but still good. Let's keep going. Here's what a period of 0.54 days sounds like. Hear how it starts to fall apart again? So we know that the period of the data is likely between 0.52 and 0.53. After playing around with the data a bit, we discover that, for this object, a period of 0.526 is what matches the data. Listen. Hear how distinct the increases and decreases are? Now that we've found the period of this light curve, we have a better understanding of the nature of this variable object. Thanks for watching and listening, and I hope you found this helpful. This video was produced by Geneva Lake Astrophysics and STEAM Education. Contributors are Shiloh Miller, Mari Lucero, Emily Sisko, Kate Meredith, and Sophia Lawton, with funding from National Science Foundation Award Number 2013300, Our Place in Space. The script and structure of this video borrow heavily from the video What is Period Folding? By Aaron Lacluse of Central Michigan University. Lacluse's video is available on Skynet University YouTube channel. The model data used also originates from the same video. The sonifications were made using Astronomy, a program developed by the Space Telescope Science Institute.